Okay. Okay. Anyway, let's just go through this, and we're gonna go through it quickly. I'll still try to stick to the time we're supposed to stop for this session. In case we talk about something interesting.
Yeah.
All right. So, I think Hudson, you already went through the slides, but since both of us are here now, um, do you like give like a summary of what this first video was talking about?
Yeah. I think this video is more about giving a summary of what neural network is. Like when it tends to get employed. I think it started from assignments. Like they were given assignments before they got introduced to neural network about recognition, about how our phones kind of operates and stuff like that. Yeah.
Right. Yeah. So, can you hear the video from my screen?
No.
Okay. I don't know why, but I think the audio doesn't ever play here. Anyway, yeah. So, yeah, the video just introduces us to the concept of a neural network, right? And in this case, the context is we're trying to, or at least the main example that's being used is the example of classifying um, some images. Then, so we have this graphic which sort of shows us the structure of a neural network. So it has a bunch of layers, and um, each layer has a bunch of neurons, and then each neuron can affect a certain other neuron that it's connected to in a different layer. And so what happens is, of course, the neural network receives something like an image in the input layer, and then depending on certain hyperparameters, which we're going to look at, it then chooses to activate or not activate, and then that affects neurons in other layers. And so you have um, you have some individual neurons which are observing some low-level pattern, and then groups of neurons can then come together and observe a more complicated pattern. And so ultimately, we can use the entire neural network to be able to differentiate between a dog and a cat, for instance. So here we see like the an example of what we call an artificial neuron. So it's going to receive an input, and then that will pass through some activation function. Then, if the answer is yes, it will activate, and if it's no, it will not activate. So the activation function is kind of like a conditional statement in this case. Most of the time, the activation function is going to be thought of as if the if the output from some calculation is greater than some number, it's going to activate. If it's less than a number, then it won't activate. And that number is typically called the bias. So here, as an example, the input is 5, and then the calculation or the activation function simply checks if the input number is less than 10. In this case, 5 is less than 10, so it activates the neuron. And over here, the input is this grid of squares, and we're looking at this region in the middle. And the activation function asks, does it have a curve? In this case, it doesn't have a curve, so it doesn't activate the neuron. So this is essentially what each and every of the neurons in the neural network is doing. Each of those little dots is doing a kind of computation like this. And when they come together, they can make a more complex neural network. And we have something similar here. Then here, you see some common activation functions. So the one at the top is sigmoid. It basically outputs a number in the range of 0 to 1. So it takes in any number and then outputs 0, 1. And then bottom one is called ReLU, and it takes in a number. If the number is negative, it's going to output 0. It still outputs 0 at 0. And then if the number is positive, it just outputs back the number. So depending on your use case, you might want to use one activation function over another one. So they are pretty interesting to look into in their own right. Now, here you see an example of a neural network in action. So it receives an input image, and as the input is passed along the layers, we can see that the neurons, they start to recognize some of these complex patterns in the shape of like a dog versus the shape of a cat. And in this diagram, the thickness of the line represents the weight of the neuron. That's like how much that particular neuron is going to factor into the output. And then green is just positive while the orange is negative. So it receives this picture of a dog and a cat, and then it passes through different neurons, and these neurons sort of, they look for certain patterns that the image has. And if the image has that pattern, then the weight of that neuron is high. So it gets fired, and it transfers that information to the next layer. And if that pattern is not really there, then the weight is small. So it's a very thin line. And let's see. So here, what we have is an example of a neural network that's just going to do some classification. So this is supposed to attempt to split the orange dots from the blue dots. And in this example, there's an input layer which just has this X1 and X2. That's the vertical and horizontal division. And then there's some hidden layers. So the other two layers are called, well, technically the second one is a hidden layer, and then the third one would be like the output layer. But yeah, the layers after that are like the hidden layers. And so what we can see here is that we started off with just being able to divide the dots vertically and horizontally. And then we can take a combination of those so that in the second layer with 4 neurons, we can now like have a slanting division where we can divide through a slanting line. So neural networks sort of build on combinations of neurons like this. And you can see the output here. Right now, it's not really doing anything. It's not really separating what we're supposed to be doing that. So it's not separating the orange from the blue because it's not. I believe the training hasn't gone through much progress yet, and it's not. You can see the weighting of the separation is not much. So here we're just highlighting the different parts of this neural network. So we have the input layer, which takes in what we call features, and yeah, I believe we talked about features in the last session here. But yeah, features are just the variables which we're using to predict something about the inputs, and those are the hidden layers, as I mentioned earlier. Then we're supposed to actually do these playground exercises and see what we come up with. So let's do this for the next, let's say the next 2 minutes. Let's do the first one. So Gutson, you can open the link and we'll go through that and then we'll talk about it. So do the first two problems sort of, and then we'll talk about what we did. Have you done the first one? I cannot hear you, by the way. I think you're muted.
Okay, yeah, yeah, yeah. I'm still going through the task, and
Okay.
my observation is that when I had like lesser number of neurons in each hidden layer, I tried for two hidden layers, and it seems that the test loss seems and the train loss seems to be like constant, still 0.5. Then when I increase the number of layers to three, also another thing I want to mention is that and when I use the activation function to be just linear, it has a higher test loss. But when I use nonlinear function like relu, it gave me a better loss of 0.3. Yeah.
Mm.
But when I use another nonlinear function like sigmoid, it went back to 0.5 test loss. So I was able to see like the variance in how the activation function affects the training and the test loss as well.
Okay. Yeah. Yeah. Interesting. Um, okay. That sounds nice. So you can do that and then play around with the second one as well.
So I'm done with the second task, and
Okay.
I observed after around like 4 to 5 times, I observed that in the task one, which is using having the number of hidden layers to be just one, and with the activation of function being relu, I observed that the shape keeps changing and the test loss, like depending on, since we keep resetting after every like iteration, we the shape keeps changing, and the why the shape keeps changing based on what was initialized as the features, as the train data sets, based on what was initialized, the shape keeps changing, and as it keeps changing, the train loss the also keeps changing, and also the test loss. Sometimes there seems to be overfitting. That is when the train loss is sorry, that is when the test loss is kind of more than so that is when the train loss is more than the test loss. But when I increase the number of of the layers to three, then I use the same parameters I used like in the previous task to like number of neurons in on the first hidden layer is three, the second was three, and the third one was two. Then with rel will be in the activation function. I the shape that keeps changing, they kind of converge to like two different shapes only. And the first shape was more like should I is this someone like a linear line, not actually linear, but when it has that shape, the loss was around 0.3 or 0.2, yeah. But when I use but when I initialize it again, it gives a another constant shape whose loss was around 0.12 or 0.17. So from those short from this task, I observed that based on the initialized data we use in training our model, we can have different results, different train and test loss, and also overfitting also influences our result as well.
Yeah, yeah. So that's exactly right. So the first activity was just on was just to introduce you to neural networks in general and making a basic neural network and then trying to see if you can get the test loss as low as possible. By the way, I don't know if we talked about loss in the previous in the last beginner session, but um, you know what loss is, right?
Yeah, yeah, yeah.
Mm.
More like the accuracy, like how it differs from the real predictions, the real values.
Right. Yeah. Exactly. So, uh, so we've learned a couple of things from those two activities. So first of all, that very often adding neurons and adding layers can help to improve the accuracy of the neural network model. And we might also want to have a set of training data that is as representative as possible, because as we've seen, very often the results we get depend on the training data that we have. So if we have the training data that is not varied enough, we might have results that are less than what we expect. And I think that sort of makes sense based on um, what we've been talking about. Since the whole point of this is that we're training this model is only going to learn as good as the training data that we give it. So if your training data is not varied enough, you're going to be having, very different results each time you try to run the network or make a prediction or something. And so that's something important to keep in mind. Now, for the third one, we're supposed to be trying to fit the spiral data. So let's do just that one for like the next 2 minutes, and then we'll move on to the next set of activities.
I've gone through the spiral nets, and
Okay.
what I observed was also variability based on the feature engineering we do. For example, when I increase the number of layers, maybe to like five, four, in sometimes when with a high number of layers, the the accuracy improves, but sometimes when it gets higher than that, it kind of decreases again. Also, even we still in some higher layers, higher number of layers, maybe in each layer, if the number of neurons also increases, the accuracy increases as well. For example, I think I tried for eight neurons. Sorry, I tried on six neurons in I think the first hidden layer, then I think also in the second hidden layer, then I think the accuracy improved a bit. But sometimes when I created more layers and also I increased the number of hidden sorry, the number of neurons in each layer, I observed that the model tends to overfit as well,
Right.
since so that I can just so that you could get the accuracy. Also, then in the second task under the spiral net, where we are to include sine x1 and sine x, sorry, is it x2? Yeah, sine x2. um in that part as well, I think there was also variability, because initially I changed my learning rate from from the initial 0.1 to 0.03, and I saw that the way it kind of trains, the speed at which it trains is to actually get a converging point. um it's actually like it was slower than when we used the initial value of zero point 0.1 as the learning rate. So I feel that the feature engineering we do while training our model affects, first of all, the speed at which our model is trained, and secondly, it also affects the accuracy at which we get our results.
Yeah, yeah. So that makes a lot of sense. Um, right. So this one is interesting because the data is in this spiral form, and we're supposed to try to see if we can make a model that fits this. um, for me, I think I had kind of similar results. So I tried making more layers and more neurons initially, and this ultimately produces, a complicated sort of model, which still does not completely effectively fit the data, especially with only the first two features. But then when we add the feature engineering, is when we decide to use other features. So basically, feature engineering is the process of identifying the features that are actually useful for your model, and we use that. And so when we do that, at least in my case, the test loss decreases a little bit, but it's still relatively high. So we might still have some work to do. There's also a bunch of settings which we could be playing with here, right? So there's the learning rate, which we've talked about. There's this thing called regularization rate, which we're not really going to explain, but it's another hyperparameter of this neural network. It basically keeps the the should I say the output of the loss from being too spiky or too discontinuous. And then we could change the activation function to different types and see what that does. But yeah, ultimately, one main thing to realize from this is, first of all, this is just a bunch of data that is really just generated for this use case. Very often, data in the real world is going to be kind of like this, where it's messy, and you need to train something to fit it. And so there's a lot of different things that you can do, then that also makes it difficult to know what exactly you should be doing. And that's why most of the time, training a model, it just comes down to, it's almost like trial and error. So you start off with certain settings and certain features, and then you see if you get like a reasonable accuracy or reasonable loss of value, and you probably won't, in which case you're going to go back and modify some of your training settings and probably add more data to your training set as well, with the hopes of changing it. So yeah, I think that's pretty interesting. Besides that spiral, in the same activity, there's also some other different shapes of data sets. Were you able to see them? I can't hear you.
Yeah.
Okay, yeah, nice. Yeah, so if you want, you can always play around with them, but I think we can move on here. So okay, so we got to see some of these. And okay, so this is Teachable Machine. So do you already go to this link and check out what it did?
Yeah, I did yeah, before this. But
Mhm.
I think at first it was a bit confusing because they were like you have to like put two, like there are like two divisions. Let me see if I can get it again. So I did the image parts, the image yeah, the image sample. And in the class one and class two, like I just to add image samples, like two image samples in class one. I think another one in the class two. So I didn't really get why we actually needed those class. So I trained it though. I had an accuracy of like 90, is it 98 point something. It was
Mm.
pretty high.
Yeah, yeah, interesting. Yeah. So I think that's like the actual version of, or the current version of this Teachable Machine model. The one that's here is the version 1. So we can take a look at that one right now. So the link is, uh, yeah, let me copy the link here. So the link to this version 1 is this one that I put in the chat, teachablemachine.withgoogle.com/v1. And it's just going to take us to this particular one. And so once we're using our camera to supply each of these classes with some images, and then we'll try to present that image to the thing and see if it gets it right. And the goal here is you're supposed to try to see if you can confuse the machine. So make it confused between one class versus another. All right. So were you able to confuse the machine?
Yeah, I think I was able to like a bit. Um, like I just took an image record from my webcam. Then for the class one, I think the machine was actually confused. Like he was giving an accuracy of more like a prediction value of around 20 something. It was like varying 20, 30, 40, 50, 60. While the class two, even though they were like similar, same image, they were given different like prediction values. But I think the class two was having like more like the prediction the level of prediction was more than what the class one actually gave me.
Right, right. So you gave it like similar images, but in the two different classes, class one and class two.
Yeah.
Right. Yeah. Okay. Yeah, that makes sense. For mine, I gave it like slightly different poses. So for class one, my face was kind of like this. Then for class two, I was like smiling a little bit, and so it could sort of differentiate between class one and class two. But then when my face was slightly closer to the camera, it was a little bit confused about which of them it was. So yeah. So the whole idea here is, well, what does this all mean? It goes back to the stuff we've been talking about, that our model is really only as good as what we train it to be. So if we give it training data that is not representative enough of what it's going to actually deal with, then it's going to get confused. And similarly, I think um, what you did also gives us another way which we can have a problem. It's if our training data is actually problematic. So, for instance, if your training data is mislabeled, so you're supposed to be classifying pictures of cats and dogs, but some of the pictures of cats you actually label them as dogs, then that's going to be a problem because that's going to lead to confusion of the model as well. So, being mindful of these kinds of things is key. And I believe that is all the material for this session. So, neural networks are typically very useful for things like image classification, which is the main thing that we've done in this session. We've done classification where we try to classify some dots as orange or blue, but we also done image classification in the teachable machine thing. But they're also used for other kinds of machine learning activities, not just classification, but mostly for that. So there's deep learning, which uses neural networks that are very, very deep. They have a lot of hidden layers and a lot of neurons in them to try to perform these classification tasks. And well, when is it useful? I think I've already talked about that. We've looked at what a neural network is. Then what can it do that a simpler model might not be able to do? So a simpler model, let's say a linear regression model, where we're trying to separate things using like a straight line. What can a neural network do that a linear regression model can't easily do?
Yeah, I think it's for that question. For example, those image classification you just mentioned. Yeah. First of all, like the way it kind of takes in an image could be like a kind of should I say a different kind of form of data, more like for example, let's say an image of a dog. Yeah, like the ears has its own way of like of representing it, the eyes, maybe the tail, whatever. Now, in a simpler model, I don't think they'll like a convenient algorithm, or more like a convenient way of actually importing the of accepting the data, then maybe transforming the data, like connecting different neurons to and through to connecting neurons through or through layers. Because in a simpler model where we don't actually use neural network, where we just do basic let's say XY features, XYZ features, and we just apply activation function. Yeah, they'll actually be able to give us like a better prediction, unlike complex images, like images of humans, or even animals, or maybe buildings, or even like trying to like read text from maybe magazines and maybe books. So I think a neural network, they actually have ability of doing that, unlike simpler model. Even though simpler model, maybe they can do a bit of let's say classification of maybe this that this is this, or maybe like this is the pattern I observed over like a period of time. I think those are what they're actually limited to actually doing simpler tasks, and not brain tasking tasks, maybe recognizing images. Because neural network, I think it was actually like fashioned according to the way the humans think. I think that's where the neural part comes into how, like, over time, it tends to
Mhm.
recognize images, people.
Yeah,
Yeah. So I think neural networks more like a mimic of the human brain, and a simpler model won't actually be able to do all that.
yeah. That's exactly right. And of course, all this versatility that they offer us, it also comes at the price of it's there's a higher computational cost using neural networks because we need to perform a lot more calculations and comparisons to actually do these things. And of course, state of the art models, they contain like billions of parameters in their neural networks. And to even make a prediction, it takes a lot of computations to do that. And so it's a good thing that these days technology is really improving. So much so these days you typically use GPUs to train neural networks, to sort of speed up the process because it can take quite a while. The fourth question is, what's the limitation of a neural network or ML in general? And I think we also sort of hinted at that earlier. So we talked about, if your data isn't good, either because it's not representative of the kinds of things that a neural network is going to be dealing with, or if it's labeled poorly, then that can be a problem for your model because your model is going to have a bunch of mistakes and a bunch of errors. Um, but yeah, I think that is everything for this session. Do you have any questions or anything you want to talk about before I stop recording?
Not really.
Okay, sounds good. All right.